ಹುಡುಗರು 14 ಜನ ಅಷ್ಟೇ ಇದಾರಲ್ಲೋ ಸಾಯಿ ಸ್ಮರಣ್.
ಇನ್ನೊಂದು ಮೀಟಿಂಗ್ ನಡೀತಿರ್ಬೇಕು ಸರ್.
ಇಲ್ಲ ಕಣ, ಇನ್ನೊಂದೆಲ್ಲ ಮೀಟಿಂಗ್ ನಡೀತಿದೆ. ನಾನು ಒಂದೇ ಓಪನ್ ಮಾಡಿದ್ದೀನಿ. ಅದೇ ಕ್ಯಾಲೆಂಡರ್ ಇವೆಂಟಿಂದಲೇ ನಾನು ಓಪನ್ ಮಾಡಿದ್ದೀನಿ. ಚೆಕ್ ಮಾಡು, ಬೇರೆ ಕಡೆ ಇದ್ದಾರೆ ಹುಡುಗರು.
ಸರ್ ಎರಡು ನಡೀತಿದೆ, ಇನ್ನೊಂದು 19 ಜನ ಬೇರೆ ಇದರಲ್ಲಿದ್ದಾರೆ.
ಯಾವ್ದ್ರಲ್ಲ ಇಲ್ಲಿ ಮತ್ತೆ ನಂದ್ರಲ್ಲಿ ಬರೀ ಒಂದೇ ತೋರಿಸ್ತಾ ಇದೆ. ನಾನು ಒಂದರಲ್ಲೇ ಜಾಯ್ನ್ ಆಗಿದ್ದೀನಿ.
ಸರ್ ಎರಡು ನಡೀತಿದೆ.
ಹೌದಾ?
ಹೇಳ್ತೀನಿ ಸರ್.
ಅವ್ರಿಗೆಲ್ಲ ಹೇಳಿ ಇಲ್ಲಿ ಬರೋಕ್ಕೆ ಜಾಯ್ನ್ ಆಗಕ್ಕೆ ಬೇಕಾ? ಟೈಮ್ ಆಯಿತು. Okay. So meanwhile, let the students get joined. So I'll just start with today's session. So in the last class, we were discussing about the class B amplifier. So in this class B power amplifier, which is considered, so we were having the we were having a complementary emitter follows stage. So that is we were having both NPN as well as a PNP transistor. So we can see before going to start with class B. So we know that class B output stage for amplifier, the Q point will be selected at the cutoff region. So whenever we are going to select the Q point at the cutoff region, then obviously, so in the class A amplifier, will be getting the full output cycle for a given input. Full cycle of input will be getting full output cycle if the Q point is selected at the center of the load line. Whereas in this case, what we are going to do, so here in this case, we are going to select the Q point at the cutoff region. So whenever we are going to have the Q point selected at a cutoff region, so obviously for a given input cycle, only positive half cycle of the output will be getting, negative half cycle will get skipped off. So because of that, so class B power amplifiers will be considered as only the operating angle is going to be only 180 degree. So in order to get the complete output, so what we need to do, so we are going to consider another amplifier, class B amplifier, which is going to work with the negative half cycle. So whenever it is going to operate with the negative half cycle, so obviously then the output of the output is going to get for the negative half cycle, so it is also going to be 180 degree itself. So when you have both the class A, class B amplifier, both amplifier which is going to work with respect to positive peak as well as the negative peak, so you will be getting the complete full cycle output you will be getting. So for that to realize, so in order to get the complete full cycle, so we are going for complementary pair of transistors which is going to work. So for that we are going to have NPN transistor which is going to be derived the power supply from the VCC. At the same time, so PNP transistor which is going to derive the power supply during the negative power supply will be given. So for a given input, so it is about instantaneous value of the input voltage will be applied to both of the bases. So whenever the input voltage is just greater than the base to emitter voltage, then obviously, so then only the output you are going to get at the then only the transistor will be turned on, and it is going to cause the current to flow across the load resistance. That is IN is the limit of transfer current IN will be flowing across the load resistance RL. So whenever the input voltage is greater than VB, that is base to emitter voltage drop in the ಜಾಸ್ತಿ ಇದ್ದಾಗ, so then only you will be your output is going to get follows with that of input, because it is going to be same as this. If you consider Q1 transistor and the load resistance, so you can see this is the bottom emitter follower stage, and hence the output is going to follow the input. So for that to happen, so input voltage must be greater than VBEN. So during the positive cycle, when during the negative cycle, during the positive cycle, since the same input has been given to the PNP transistor as well, so this PNP is going to be operating in cutoffs, because the base to emitter voltage drop will get reverse bias in this case, and whereas base to emitter will get forward bias. So because it gets forward bias, the output voltage will be getting follows as that of input, whereas this voltage will reverse bias the QP transistor, that is NP transistor and PNP transistor. So this will be in operating in cutoff state. So since it is operating in cutoff set, so only the output you will be getting from this load current is going to flow across the load resistance because of the Qn, hence it is going to work with respect to positive half cycle. So during the negative half cycle, so this Qn will become reverse bias, and because of this VBN will be reverse bias, and when compared to that of QP. So in that stage, the QP will be acting as a emitter follower. So during the negative half cycle, so during the positive half cycle only the Qn will be working, so that you will be having 180-degree of output will be getting. That is during the positive output will be getting. Whereas during the negative half cycle of the input, so your PNP transistor will be on and the QN transistor will be off. That means the NPN transistor will be off, PNP will be on, and because it is on, so this will be operating in linear region, and hence it is acting like another emitter follower concept. So since it is going to follow, call it as another emitter follower. So output is going to follow with respect to input. So negative input of the signal is going to follow with respect to the output. So output is going to follow the negative cycle of the input signal. It is going to follow. So it is nothing but a emitter complementary pair. So complementary pair, why? Because when Qn is on, QP will be off, and when Qn is off, QP will be on, and hence both will be operating. So either one of the transistor will be operating with respect to the input signal. Hence, so because of the opposite in characteristics of this NPN and the PNP transistor, hence it is named as a PNP, so complementary pair. At the same time, so complementary pair transistor, because both our device characteristics will be opposite to each other. And hence we have seen, so the transfer characteristics for this class P amplifier also we have seen. So what is the transfer characteristics which we have seen? So this is a transfer characteristics curve for the class P amplifier. So we know that Qn will be operating with respect to positive half cycle, and QP will be operating with respect to negative half cycle. So during the positive half cycle of the input, so input, as you increase the input voltage greater than 0.5, then only your output is going to follow the same as that of input. So in order to make the output to follow to that of input, that is emitter follower. So we know that here the slope is given as 1, indicating that so it is output is going to vary with respect to inputs, and output and input both are same, nearly equal. So we are going to get the slope as equal to 1. So you will be getting the slope as equal to 1 when, so whenever the input voltage is greater than 0.5. So what is this 0.5 voltage? This 0.5 voltage corresponds to the base to emitter voltage of the NPN transistor. So whenever the input voltage is greater than 0.5 volts, then only your output voltage is going to be linearly proportional with respect to input voltage. And hence whenever the input voltage is greater than whenever input voltage is greater than the collector to emitter voltage, then the transistor will enter into saturation, and because the transistor enters into saturation, the output will get saturated. So output will get saturated to the positive swing, which is will be equal to VCC minus VCN sat. So this is as illustrated over here figure. So up to here you can see the slope is equal to 1. And now when the input signal is in the negative half cycle, so whenever the input signal comes less than 0, it is nothing but a negative half cycle. So minus 0.1, 0.2, 0.3, minus 0.1, minus 0.2, minus 0.3, like that. Whenever the input voltage exceeds in the negative direction greater than minus 0.5, so that is minus 0.6, minus 0.7, like that. And whenever the input voltage is greater than minus 0.5, then your output is going to slowly it is going to increase, and with respect to increase in the input voltage, and hence you can see a slope which will be equal to 1. Okay. So this is how we are going to get the slopes, and as soon as the transistor PNP getting saturated, so the output is going to follow to that of input, and it will get saturated in negative saturation direction, that will be equal to minus VCC plus VCEP saturation. So this is what the transfer characteristics. When you look at this transfer characteristics, you can see in the region between the minus 0.5 to plus 0.5. So you can see for any changes in the input within this range, so between the minus 0.5 to plus 0. So you are not getting any output. So that means output is stuck to 0. So stick on to 0. Hence this band is called as a dead band. So for any input voltage, you are not getting any output. So this band, this portion of the input signal, so output is stuck to 0. Hence it is called as a dead band. And when you look at the output voltage during this range of operation, minus 0.5 to plus 0.5 input signal operation, you can see the output will be 0, and you can see some crossover distortion. So this is the transfer characteristic what we have seen over here. So same transfer characteristic V0 versus Vi, it is being plotted over here for the class B amplifier, and this is the range wherein which the output is for any input signal, so output is going to be equal to 0. And then after that you can see there is increase in the positive direction as well as in the increase in the negative direction. So when you look at the output voltage in this corresponding case, so this is nothing but input voltage, right? So this is the input voltage. So whenever this is the input voltage and this is nothing but the output voltage which you are going to get. So during this portion of the input, the portion of this input signal, you will be getting the output. Whereas during this dotted line between the minus 0.2 plus 0.5, which is nothing but this dotted line. So during this range of input, will be getting the output as equal to 0. So this indicates what? So during this amount of the input signal, so you are not getting any output. After that again during the negative half cycle, so you will be getting the remaining portion of the negative half cycle being produced at the output side. So this about the negative half cycle, and then the positive half cycle it is going to repeat again during this region. So this kind of output wherein which you will be not getting any output during this range is called as a crossover distortion. Why it is called crossover distortion? Because whenever the input is going to switch from positive power supply to negative power supply or negative to positive power supply, so you are getting the output getting stuck to 0. So hence it is called as a zero crossover distortion, or also simply called as a crossover distortion. So crossover distortion means so input signal or the output signal whenever it is going to cross from output to input, because since it is input as well as output is both are same in the case of emitter follower. So either you can consider, so whenever the case of input is falling from positive to negative or negative to positive, similar to that of output getting changing from negative to positive or positive to negative. So you can see there is you are not getting any output. So that is called as a distortion. That is called as a zero distortion or crossover distortion. So that is the only drawback which you are going to find in the class B amplifier. So now in order to find out the efficiency, so for any classification of the amplifier is considered, so you require, so the circuit diagram should be written. So after that transfer characteristics must be there, and power conversion efficiency must be there, as well as power dissipation. So these are the four important points that you need to be considered, or you need to be remembered when in any case of classification of amplifier is considered. So class A as well as class B. And then if we consider this power conversion efficiency, so power conversion efficiency is given by the expression what? So eta. So eta will be equal to AC power delivered to the load over DC power supply. So that is given. So first we need to find out what is the AC power delivered to the load. So that is given by load power. So PL. So that will be equal to, so V0 cap divided by root 2. So or else you can say that what is the maximum peak voltage for that output voltage is given. So that we are going to consider. So load power will be equal to V0 cap divided by root 2. And for load power is considered, so V0 cap divided by root 2 whole square divided by RL. So that is nothing but this is one of the formula that you need to remember for the load. So P can be equal to V square by RL, or P can be equal to I square into RL, or P can be equal to V into I. So in this case we are going to consider this PL in terms of V square by RL. So V0 is nothing but output peak of the output voltage, V0 cap divided by root 2, that is the root 1 square when you are going to calculate. So in terms of peak signal, so V0 divided by root 2 you are going to calculate. So V0 divided by root 2 will be the output voltage whole square. It will be giving as V0 square divided by 2RL. So this is the load power. And now in order to find out the AC supply power to the load, so this is the load power. Now in order to find out the DC power supply, so that is a DC support supply which is because of the supply voltage DC. So we need to find out what is the PSL. So there's a supply power we need to find. So in order to find out the power supply, so we know that in this configuration, so in this circuit configuration, you can see there are two power supply are there. So one is positive power supply is there, another one is a negative power supply. And during the input cycle being in positive half cycle, so you are going to supply the power from the positive, and during the negative half cycle of the input, so you are going to be supplied the power from the negative power supply. So we are going to have expression. So supply power will be consisting of both positive as well as negative power supply. So that is going to be defined over here. So PS plus indicates positive power supply and PS minus indicates a negative power supply. So in each of the case, what will be the case of output? So output will be having what? So it will be having starting it will be distortion, and then you can see the output during the positive cycle, and again it will be zero. So that means the output of voltage. So what is the current which is going to be drawn taken from this time is so maximum voltage is VCC, and what is the current drawn is nothing but V naught cap divided by RL. So this is the V naught cap. So I is equal to V by R. So we know to find out V into I. So that is the supply power. So I we need to find out. So I will be given as what? V naught cap divided by pi RL. So instead of RL, so you will be having pi RL because for a given positive power supply only for 180 degree. So up to pi radians you are going to have the output to be appear over here. So I am going to have a current will be equal to V naught by pi RL. And the remaining during the negative power supply, the same thing the same equation holds good for the negative power supply. So it is also equal to V naught by pi RL. So that is the amount of current drawn during each of the power supply. So we need to find out the power supply now. So in order to find the power supply, I need to know what is current and then what is the maximum voltage. So then you multiply with the voltage with the current equation, then you will get what is the power supply. So first we need to find out what is power supply with respect to positive and the negative. So first positive power supply and negative power supply will be both will be same. It will be equal to so current expression, right on the current expression. So current expression is given by V naught by RL, V naught by pi RL into what is the maximum power supply, maximum voltage which you will be getting, that will be equal to VCC. So V naught by pi RL into VCC. So for both the negative power supply and then the positive power supply, we will be getting this. So what is the total DC power supply which is going to be done? So you have to add these two. So positive power supply plus negative power supply. So it will be equal to 2 by pi V naught by RL into VCC. So this is the total supply power delivered to the delivered from the total DC power supply delivered. So PS will be equal to 2 by pi V naught by RL into VCC. So this now I got to know what is the power supply delivered, and now what is the power supply delivered to the load I have found out, and also DC power supply also I have calculated. Now I can easily find out what is the efficiency, conversion efficiency. So it is nothing but AC power delivered to the load over the DC power supply. So take the ratio of these two. So V naught square divided by 2 RL into 2 V naught cap divided by pi RL into VCC. So that will be equal to which we will calculate or simplify it. We will be getting the pi by 4 into V naught cap divided by VCC, and the output will be maximum when we will be getting. So V naught will be equal to VCC. So VCC will get cancelled. Pi by 4 will be getting. So this is the maximum efficiency for a class B amplifier. So this class B amplifier will be having the 78.5. So in the class A amplifier, how much the maximum efficiency was there? So in class A amplifier, the maximum efficiency was equal to 25%. Whereas in the class transformer coupled class A amplifier, what was the maximum efficiency? Conversion efficiency. The maximum conversion efficiency has been increased up to 50%. So neta will be equal to 50% in the transformer coupled class A amplifier. So if you consider class B amplifier is considered, so using the emitter complementary emitter pair transistor, so you are going to get the efficiency which will be equal to 78.5%. So which will be greater in terms of compared to class A amplifier is considered. So you can see the efficiency will be greater, it will be equal to 78.5. So now what will be the maximum power supply voltage? So what is the load of maximum power load supply we will be getting? So if I supply for this V naught with a VCC, so it will be reaching maximum up to output voltage will be reaching maximum up to VCC. So PL will be equal to VCC square divided by 2RL. So that will be the VCC square divided by 2RL will be the total load power maximum will be getting. So in order to find out the power dissipation, so in order to find the power dissipation, not in unlike in the common class A amplifier stage is considered. So there you are going to have a quiescent power dissipation was there. So that was the maximum power dissipation when Vi was equal to 0. So you will be getting that quiescent power dissipation, which will be equal to VCC into I. So that means that was the maximum. But when you consider here, so in the class B amplifier is considered, so at when Vi is equal to 0, so output will be equal to 0 itself. So we have seen the dead band, right? So in dead band, what is there? So until minus 0.5 to plus 0.5, whatever the input you give, so output will be 0. So that indicates that you will be not having any such power dissipation in this case for class B amplifier is considered. So whenever the input signal is applied, so average power dissipation will be calculated based upon the difference of supply power and the load power. So that is the power dissipation. So calculation. So supply power minus the load power. So this supply power is nothing but a DC power supply, and PL is nothing but a AC power delivered to the load. So if you subtract these two, then you will be getting the power dissipation. So in this case, so power dissipation, we have to write down the corresponding equation over there, and in order to get the find out the value, what will be the maximum power dissipation, you need to differentiate the output voltage, peak of the output voltage with respect to you need to differentiate this equation 13.22. So with respect to V0, so output voltage we need to differentiate, and then we will be getting the maximum power dissipation. So worst case power dissipation we will be getting. So worst case power dissipation is the name of maximum power dissipation itself. And you can see we know that power dissipation is occurring because of what? So because during the positive power supply as well as negative power supply, because of transistor Qn as well as Qp respectively, because of complementary pair was in the. So during the positive half cycle of the input signal, so half of the power dissipation will be exhibiting from the contributing from the Qn transistor, and another half of the power dissipation is going to be contributed from the Qp transistor. So if you calculate the power dissipation, then it will be the total power dissipation. So if you divide by 2, then it will be the power dissipation with respect to each PNP as well as NPN transistor respectively. So we are going to represent the same thing, and you are going to find out the differentiate that expression with respect to V0, and you are going to substitute that value equal to 0. Then you will be getting the worst case, that is the maximum power dissipation for the output voltage will be equal to 2 by pi times of VCC. So 2 by pi times of VCC, that will be the maximum power dissipation. And then so if you substitute in the value of PD max, so you will be getting so V0 expression. So V0 you will be getting 2 VCC square by pi square into RL. So this is the power dissipation. So maximum power dissipation you will be getting, and divide by 2, it gives the power dissipation with respect to each PNP as well as NPN transistor respectively. So we are going to divide the equation 13.24 by 2, so that we will be getting the power dissipation maximum for NPN transistor as well as the PNP transistor will be equal to VCC square by pi square into RL. So this is about the power dissipation, and if you find out the expression with respect to power dissipation with respect to the output voltage is considered, so you can see this is the output voltage. So output voltage, peak of the output voltage will reach up to VCC. So between the 0 to VCC you will be getting the 2 VCC by pi. So that is 2 by pi VCC, that is it will be less than the VCC itself. So at that corresponding point of equation, we will be getting the maximum power efficiency, power dissipation, and as well as the efficiency during that period will be equal to 50% obviously. So this is the power dissipation. So this is about maximum power dissipation. And when the input voltage, when the output voltage reaches to the peak of VCC, so you will be having the efficiency better. So that will be equal to 78.5%. So with this, we have just concluded in the last class about the class B amplifier is considered. So now we will go to the next stage of the amplifier, that is nothing but class AB output stage of amplifier. So class A amplifier, transformer coupled class A amplifier is over, and class B is over. Class A only what things we have learned. So the efficiency was equal to 25. Transformer coupled only 50% efficiency. So class B output stage of amplifier only 78.5. It has been increased. So one drawback in class B amplifier is so you are going to have a crossover distortion. So that crossover distortion is the only drawback. So if we eliminate that crossover distortion, the output voltage cycle, so as well as the you will be getting the full cycle output as well as the efficiency you can able to increase in this corresponding as well. So for the to avoid the class B amplifier, that is a crossover distortion, that is because of the base emitter voltage drop. So we are going to consider the class AB output stage. So in this class AB output stage of amplifier, if this is considered, so it is a compromise between the class A and class B amplifier. So that is it is going to have in between the class A and class B, wherein which the output will not be full, complete output will be not getting, whereas the output will not be partially half also. So it will be not equal to half, or it will be not equal to full. That means in between the half and full, so whatever the output you will be getting. So that output you will be getting in the case of a class AB amplifier. So how we are going to get this class AB? It is partially. So we have to see. So because how we are going to see that output will be in between the class A amplifier and class B is, so it will be greater than 180 degree and less than 360 degree. So that means it will be greater than 180 degree means greater than class B amplifier, and less than 360 means it will be less than class A amplifier is considered. So it is called as a class AB amplifier. So in order to get that output, so that is greater than 180 and less than 360. So sorry, so we need to bias the operating point. So that is a transistor or the amplifier which is considered, so it needs to be bias the operating amplifier to be greater than cutoff and less than the center of the load line. So that means if the operating point is below the center of the load line and above the cutoff point, so that means the output you will be getting greater than 180 and less than 360 for a given input signal. So that is the operating angle of class AB amplifier is considered. And now we can see the circuit diagram for the class AB amplifier stage. So it will be resembling same as that of class B amplifier is considered. So complementary transistors will be considered over here, QN and QP transistor, and QN is going to be driving the load during the positive half cycle, and QP will be driving the load during the negative half cycle. So as same as that in the previous circuit. So this was same, right? So this is the same, and we'll be having positive power supply voltage as well as the negative power supply voltage was there. So another thing is that input was connecting for both the input of the base of the transistor Q1 and QP. So whenever we are going to have this type, so only thing we are going to in this amplifier is changed is the DC power supply voltage, DC bias voltage, which is being connected to both of the transistor QN and QP. So what is the advantage of connecting this DC base voltage? So VBB is nothing but base voltage, so which is going to be connected as DC input to the transistor Q1 and QP respectively. So in this case, what will happen? So in this case, since the VBB by 2 is going to be connected in series to the base of the transistor Qn. So whatever the base to emitter voltage drop was there, so for a transistor Qn, so VBEN, so whatever the base to emitter voltage drop was there, so that will be overcome by this connecting the voltage VBB by 2. So this is a positive voltage. So this positive voltage will be made such a way that it should be equal to it will be made such a way that it should be equal to the value of the base to emitter voltage. So whenever it is being done, so now whenever you increase the input voltage from starting from 0, so when the input voltage will start increasing, so you're going to add along with VBB by 2 your input voltage, so that the output voltage also is going to increase in the linear way. So starting from the 0 itself, so 0.1 voltage if I'm going to give, so you'll be getting the output voltage as 0.1 because it is a emitter follower configuration. And since VBB by 2 will be adding as a bias voltage for the QN transistor, so the same reverse bias voltage will be applied for the QP transistor as well. So whenever VI is applied, so for both QN as well as QP, both will be provided. So during the positive cycle, it is going to increase the value of the current that is going to flow over the transistor Q1. At the same time, it is going to reduce. So here it will be forward bias between the base and emitter, whereas here it will be reverse bias between base and emitter junction during the positive half cycle. So because of that, QP is going to be the value of the QP transistor will be that is it will be operating in cutoff stator. So QN will be operating in the linear region, whereas QP will be operating in cutoff region. So with the input voltage, so you will be getting the output voltage starting from 0 itself. So whenever the input voltage is increasing, at the same time the output is also going to increase. At the same time, so when VI becomes negative, so that the VI will be reduce the input voltage of the base to emitter voltage of Q transistor, and hence base to emitter voltage of the QP transistor is going to reduce, and then QP transistor, and it is also going to act as a emitter follower in the reverse way. So during the negative half cycle of the input, hence you are going to get the output which is going to proportional to that of input voltage starting from zero itself. So as soon as you increase in negative direction, so the output is also going to increase in the negative direction itself. So this is the current expression which is going to be useful in this one. So IN and will be equal to IP because QN and QP both are made up of complementary resistors, so which is going to be remain same. So the current which is flowing in IP QP will be equal to IN, and I in the transistor QP will be equal to IP respectively. Both will be same, and the value of IQ, that is the quiescent point voltage, will be equal to IS into e power VBE by 2 times of VT. Why it is 2 times of VT? So VBE divided by VT will be that, right? So VBE is given with the bias voltage as VBB by 2. So VBE by VT, that corresponds to VBB by 2 times of VT. So this is the current, that is the expression which is going to work with respect to both the transistor QN and QP respectively. So circuit operation ಮಾಡಬೇಕು ಅಂದ್ರೆ, so we need to explain about the circuit operation ಅಂದ್ರೆ. So in this type of circuit operation, what is we are going to get is, so during the input voltage, whenever the input voltage is greater than VBB by 2, so that means so whenever the input voltage starts increasing from 0, so you are going to get the output voltage. So output voltage will be equal to what? So VI plus VBB by 2, which minus of VBN. So VBN, so it is the base emitter voltage drop of a 10 N transistor. So VB by 2 minus VBN. So you'll be getting V0 will be equal to VI, because provided that the base DC voltage which you are going to give VB by 2, if it is equal to VBN. At the same time, so whenever the device QN is on, so what is the value of QP? So IP. So QP will be equal to cutoff, and IP will also be equal to 0. So only current that is flowing inside the MOSFET will be equal to IN. So IN will be equal to IP plus IL. So IN will be equal to IP plus IL. So the increase in the IN, there is an increase in the QN transistor current, so causes a similar decrease in the current in the IP in the QP transistor. So increase IN will accompanied by the corresponding with the VBN. So whenever, since the voltage of the both VBN is given with constant DC bias voltage which will be equal to VBB. So VBB is the voltage, so which is going to have half of the VB will be given to QN, and another half will be given to the VBB negative. So you can see there are two bases remains constant at VBB, and hence the VBN will be equal to VBB P, and VBN N, VBN plus VBN plus VB will be equal to VBB. So provided that if you are going to support, VBB will be made is equal to base to emitter voltage of N transistor and base to emitter voltage of P transistor, then obviously, so you will be getting the output signals without any distortion. And then this shows the figure or transfer characteristics of the class AB amplifier is considered. So this is the output voltage with respect to input voltage is considered. So as soon as you give the input voltage greater than 0, so you can see there is an increase in the gain. So that is nothing but linear amplifier. So that we can say that output is going to follow the input, because it is an emitter follow stage. So the output is going to have the same as that of input configuration. So input ಏನಿರುತ್ತೆ ಅದೇ output ಬರುತ್ತೆ. So you will be getting. So this is about positive voltage getting saturated, and for negative voltage getting saturated, we need to apply the reverse voltage. So that is whenever input voltage is in negative terms, so that it will start increasing from 0 itself. So you will be having the output proportional to that of input, and during the negative, and whenever the input voltage exceeds that of the emitter, so the transfer will enter into saturation, and then it will get saturated in the reverse direction, which will be equal to minus VCC plus VCP saturation. So here VCN saturation. So positive saturation at VCC and negative saturation at minus VCC. And if we look at this expression, what is the base to emitter voltage? So VBEN, so there is a base to emitter voltage of the N transistor. So base to emitter voltage of P transistor will be made equal to VBB, right? So this value we need to find out. What is this value? So in order to find out this value, so we need to find out what is the voltage across here. So voltage across here will be equal to Vt into ln of In by Is. So this is nothing but In is the current that is flowing, and Is is the saturation current expression. So ln of In by Is, that is the value of the current that is flowing across the NMOS transistor. Same way, PMOS transistor will be given with Vt into ln of Ip divided by Is. So that is nothing but current, that is equation. So which will be equal to 2 times of Vt ln of Iq by Is, because In plus Iep will be equal to In plus Iep will be equal to Iq. So ln of Iq by Is will be getting. So In into Ip will be equal to Iq square. So this is the relation which you are going to find with respect to this expression, because we are going to remove the line term, means you will be getting the In Ip will be equal to Iq square. And when you substitute this expression, we know that equation 13.29 and 13.27, if it is considered, so you can easily find out these three equations if you consider. So then obviously you can find out the value of in the form of a quadratic equation. So that equation will be equal to In square minus In Ip minus Iq square. So this will be equal to 0. So this is the expression which you are going to get with respect to this relation, which you are going to get with respect to Vb, base to emitter voltage. So now once the current expression has been found out, so next is for negative voltage, how the transistor is going to work. So when you consider the power amplifier relationship between the class AB amplifier are almost the same as that in the case of class B. So only thing difference is we are going to employ one VBB, that is the reference voltage across the base. Reference voltage has been included. Apart from that, the rest of the circuit is the same, as well as the rest of the circuit operation is also same. And then the power dissipation in this and both will be remain same. Only difference is base to emitter. So we are going to employ one base voltage. So when you employ this base voltage, so this is going to work with respect to 0 itself, so that you will be getting the power dissipation in the class AB at 0 signal itself. At 0 signal also you are going to get at a 0 signal you are going to get the power dissipation. So the circuit powers the dissipation of VCC into IQ. So the value of IQ will be very much smaller when compared to the power dissipation which you are going to get in the case of Q-cell power dissipation in the class A amplifier. So class A amplifier only VCC into IQ it was large, whereas in this case ICC into VCC into IQ. So this IQ value will be nearly very small. It will be equal to In multiplied with Ip will be equal to Iq square. So Iq will be very much small quantity. So when it is considered, so the power dissipation in this Q-cell power dissipation is also will be minimum in this case. So if you consider the conversion efficiency, everything, so it is going to be remain same as that of class B. So only thing is the circuit diagram and how we are going to find out the how we are going to avoid the crossover distortion. So in this crossover distortion is avoided. The class B amplifier only, so class B only you are getting the minus 0.5 to plus 0.5. So your transfer characteristics only you can see the output of the voltage is not going to be it's not going to increase. So in order to say that it is a cross distortion was there in the class B, that has been avoided by connecting on base to base voltage across the base terminal. So on considering this base voltage, so this VBB by 2, so on connecting, so you are going to avoid that crossover distortion. So when you reduce the crossover distortion, you can see this is the modified circuit, so it's going to be consistent. So in order to find out the output resistance, so next important thing is that I need to find out the output resistance. So in order to find out the output resistance, we are going to find out across the emitter terminal. So from the emitter terminal, you are going to provide the output. So for this emitter terminal, input voltage. So this is the output side. In order to find out the output resistance, we have already seen how to calculate the value of the output resistance of any particular amplifier is considered. So what we are going to do? So we are going to remove all the DC quantity and we are going to make it into DC signal ground. So whereas DC power supply ಏನೇನು ಇರುತ್ತೆ ಎಲ್ಲದನ್ನು ರಿಮೂವ್ ಮಾಡಿದ್ದೀವಿ. Even VB1 as well as VB2 because of the positive power supply has been removed, and input signal source also considered to So even both DC supply sources, everything it is going to reduce to zero, and only you're going to see from the output side with the test input circuit voltage across the output, and then you're going to find out what is the equivalent resistance which you're going to see observe here. So whether my voice is audible? Okay. So in order to find out the output resistance, determine the small signal output resistance. So the resistance which you are going to see from the output side is nothing but emitter resistance. So each from the NPN as well as the PNP transistor, that is RE. So resistance RE as well as the resistance REP as well as REN is the output resistance or emitter resistance in each of the NPN as well as the PNP transistor respectively. So if you want to find out the output resistance, so this will be equal to REN parallel REP. So that will be the equivalent output resistance which you are going to get. So we need to, in order to find out the final R out, so we need to find out what is REN. So REN value, what is the REN value? So REN will be equal to what? So what is the test voltage which is connected? VT. So R is equal to V by I. So the current that is flowing across the transistor QN is IN, and across the transistor QP is IP. So REN will be equal to VT divided by IEN and IEP respectively. So for REN, VT by IN, and REP is the emitter resistance. So that is VT by IP. So if you consider REN parallel REP, so you will be getting this as the VT by IN parallel with VT by IP. So you will be getting the expression which will be equal to VT by IP plus IN. So in this expression, if you consider, so the value of IN and IP, you can see that whenever the IN is current is increasing, means during the positive cycle, IN value it is going to increase, whereas IP value it is going to reduce, because so during the positive cycle IP will be equal to 0 when considered with respect to IN value. The same way, when during the negative cycle IP value will be increasing, whereas IN value it is going to be reduced by the same amount. So so that at any instant of the time you will be getting IN or IP current will be there. So we are going to conclude that so IN and IP at every instant of the time any of the current will be there. So you are going to get a constant output resistance. Remains almost equal to constant. So the same thing has been written here. So IN increases, suppose IN increases. So IN increases ಅಂದ್ರೆ ಏನಾಯ್ತು, transistor Q1 is going to forward bias ಅಂತ ಆಯ್ತು. For a given input voltage, the current is going to increase. At the same time, so QP transistor will be in cutoff state, so the current flowing in the P transistor will be approximately equal to 0. And during the negative cycle, IP current will be flowing, IN will be absent, so that you can say that the output resistance using this expression, so at any instant of the time, so the output resistance will be constant, and the same thing you can observe in this case also. And because of the zero crossover distortion, so crossover distortion has been avoided, so the output resistance is going to be almost constant. So with this we have just concluded the class AB amplifier. So in this class AB amplifier we have not dealt with power conversion efficiency, because the power conversion efficiency will be remain same, because in the whatever the class BLN power conversion efficiency was there, the same power conversion efficiency you will be having in class AB. Only thing difference is you will be not having any crossover distortion in this class AB amplifier is considered. Whether it is clear? So this is about this concludes about the third module. So that is class AB amplifier. So class C amplifier is also there. So I will just I will just finish in the classes. I will just start with module 4. So one last topic, class C amplifier. Few 10 to 15 minutes class is there. That is class C. So that I will consider after this IA. Okay. So I will just consider finish the IA portions for the analog circuits. After that, I will just do that class C amplifier. So with this, I'll just conclude today's class. So this is about the class AB amplifier is considered. Whether you're having any doubts, so if you have any doubts, you can ask. So this completes about the module 3. So feedback amplifier along with the power amplifier. So in the module 3. Is it clear? So I have just uploaded all this content in your analog circuits course manual subject. So have you uploaded class? This is what is that? Assignment number 2. So tomorrow is the sorry, still 3 days is there. I think 26 is the last date.
Last year.
26 is the last date. So you can upload till 26. Okay. Okay, I'll just conclude today's class. Okay, we'll meet you in the afternoon with the batch 2.
Thank you, sir.
Okay, thank you.
Thank you, sir.
Thank you.
Thank you, sir.